Constructing and interpreting graphs are two very important skills that any well-educated person should have. This lesson deals with a type of graph commonly used in physical science. Upon completion of this activity, students are expected to be able to effectively convey information using XY graphs, select appropriate variables given a theoretical equation to generate a linear plot. Those students should be able to obtain and interpret the slope and intercept of a linear plot. Students should be able to determine the value of the acceleration due to gravity by measuring the period of a simple pendulum. A graph is a visual summary of the relationship between two or more quantities. The most common type of graph used in physical sciences is called XY or scatter plots. On these plots, experimental quantities are represented by points on a Cartesian coordinate system. The quantity that we deliberately change during an experiment or a series of experiments is called the independent variable. The independent variable is typically assigned to the horizontal axis, which is commonly referred to as the x-axis. The other variables are called dependent variables and are assigned to the vertical axis, which is commonly referred to as the y-axis. Interpreting an XY graph is a very important skill to learn in science. Here are some questions that you should be able to answer by examining the example graph shown here. Question 1. What are the dependent and independent variables? Values of the independent variable are shown on the horizontal axis. For the example graph shown here, the independent variable is in volume, and the units for volume is milliliters. Values of the dependent variable are shown on the vertical or y-axis. For the example shown here, the dependent variable is pressure, and the units for pressure is atmospheres. Question 2. What is the pressure measured in the experiment when the volume was set to 2 milliliters? Each point on the graph represents experimental data. The coordinates of the point represent the experimental values of the dependent and independent variables. For example, consider the second point shown here. If we imagine tracing a straight vertical line from this point toward the x-axis, we find that the point represents a volume of about 2 milliliters. If we imagine tracing a straight horizontal line from this point toward the y-axis, we find that the point represents a pressure of about 2.2 atmospheres. Therefore, this graph is telling us that during an experiment, when the volume was set to 2 milliliters, the pressure was measured to be 2.2 atmospheres. Question 3. What happens to the pressure as the volume increases? Note that the higher a point is on the graph, the higher the pressure. The farther the point is to the right, the larger the volume. If you were to draw a curve tracing the points from left to right, you would note that your hand would be moving downward. This means that as the volume increases, the pressure decreases. It is customary to draw a smooth curve, as shown in the example here, to emphasize the trend in the data. This smooth curve is also known as the trend line. Question 4. What would the pressure be if the volume were set at 1.5 milliliters? Drawing a trend line through your data makes it easy to make predictions. For example, none of the points shown in the example graph correspond to 1.5 milliliters. This means an experimental measurement of pressure with the volume set at 1.5 milliliters was not done. However, we can predict what the pressure would have been by imagining a straight vertical line from the 1.5 milliliter mark on the x-axis toward the trend line. Then, when we hit the trend line, imagine a straight horizontal line toward the y-axis. Based on this, we can interpret that the pressure would have been 3 atmospheres. What we have just done is called interpolation. Can we predict what the pressure would be if the volume were set to, say, 25 milliliters? The volume we used in the experiment ranged from 1 to 5 milliliters. 25 mils is beyond this range. Making a prediction in this case would be called extrapolation. Because the trend line is not a straight line, we cannot be sure about how it will behave beyond the range. 25 mils is too far beyond our experimental range of values. Therefore, we cannot reliably predict what the pressure would be. If the trend line were a straight line, we would have more confidence in doing an extrapolation. Do keep in mind that a trend could appear linear if an interval is not wide enough, and you may not see any significant curvature until you examine a wider range of values for your independent variable. In other words, extrapolation is generally less reliable than interpolation. You have learned in algebra that the general form for the equation of a straight line is y equals mx plus b. In this equation, x and y are variables, and we say that they are linearly related if m and b are constants. In other words, if y is equal to a constant, represented here by the letter m, times x, plus another constant, represented here by the letter b, then a plot of y versus x is a straight line. The constant m is called the slope of the line, and b is called the y-intercept of the line. The y-intercept refers to the y value when x is 0. In general, experimental quantities are not linearly related, but functions of these quantities may be linearly related. For example, the pressure and volume of a gas, represented here by the symbols P and V, are related by the equation P times V equals a constant, represented here by the letter K, at a constant temperature. This is a relationship that was discovered by Robert Boyle. We can rearrange this equation and show that 1 over pressure is equal to 1 over K times volume plus 0. Since K is a constant, 1 over K is also a constant. In other words, 1 over pressure is equal to a constant times volume plus another constant. This means if we let y equal to 1 over pressure and x equal to volume, then the plot of y versus x would show a linear trend. This is illustrated in the graph shown here. Note that because of experimental errors, we generally do not expect experimental data to line up perfectly, and it would not be possible to draw a straight line through each and every point in our graph. In general, we should not attempt to connect the dots by straight line segments. Instead, to communicate that we are trying to show a linear trend, what we do is draw a straight line that is as close as possible to all the points. This is called the best fit line. It is also useful to show the equation for a straight line on the graph. In the example given here, the equation is shown as 1 over pressure equals 0.22 times volume plus 0. We can identify 0.22 as the slope, which should be equal to 1 over K. Thus, we can solve for the value of K as 1 over 0.22. We can also identify 0 as the y-intercept. When we have a graph showing a linear relationship between two quantities, it is useful to find the equation of the line. To do this, we just need to find the slope and the y-intercept. If you are using a computer program such as Microsoft Excel, you can ask the program to display the equation for you. The example graph shown here was created in Excel. When asked to display the equation of the line, Excel returned y equals 0.2229 times x. To improve the presentation, the equation was edited to the one shown here. If you are manually graphing your data, you can determine the slope by picking any 2 points on the best fit line. In the example shown here, the points chosen are 1.80 milliliters and 0.40 reciprocal atmospheres, and 4.76 milliliters and 1.06 reciprocal atmospheres. Once we have chosen 2 points, we can take the difference in the y values of the 2 points. This is called the rise. In this case, 1.06 minus 0.40 equals 0.66 reciprocal atmospheres. Then we take the difference in the x values of the 2 points. This is called the run. In this case, 4.76 milliliters minus 1.80 milliliters equals 2.94 milliliters. The slope is just the ratio of the rise to the run. That is, the 0.66 reciprocal atmospheres divided by the 2.94 milliliters, or 0.22 reciprocal milliliters reciprocal atmospheres. How do we determine the y-intercept? Since y equals mx plus b, we can show that b is equal to y minus m times x. We plug in our slope for m and plug in the x and y values from one of the 2 points that we chose to calculate the slope. In the example here, the y-intercept comes out equal to 0. Here are some guidelines for constructing a graph that effectively communicates the results of an experiment. First of all, if you are not using a computer to create your graph, use a full sheet of graphing paper with a pre-printed grid for each graph. Make sure that you choose your scale so that the points are spread out over at least half of the area enclosed by the x and y axes. The axes need not start at 0. Pick some nice round number just below the lowest experimental value for the minimum value, and another nice round number just above the highest experimental value for the maximum value. It is also not necessary for them to cross at the origin. Note that there may be instances where you will need to extend your x or y axes at 0, and those would be cases where you would have a good reason to extrapolate the trend line. In other words, there might be some valuable information that can be obtained by extending the trend line to x equals 0 or to y equals 0. Put tick marks on your axes to divide it into equal intervals. Select an interval size that will make it easy to locate points on the grid or to read the coordinates of any point on the grid. It is good to use values of 1, 2, 5, or 10 units, or any of these times the power of 10. For example, intervals corresponding to 0.02 or 0.05 units would be good. Intervals corresponding to 30 or 70 units are not good to use. Here are some more guidelines for constructing a graph that effectively communicates the results of an experiment. Each axis should be clearly labeled. Values of the variables at evenly spaced intervals should be indicated. Underneath the values, the name of the variable and the unit should be indicated. A descriptive title that does not simply repeat the names of the variables should be included. For example, if your y-axis variable is distance and your x-axis variable is time, a title that says distance versus time is useless. If you are using a computer program like Microsoft Excel, it is better to leave out the chart title as it tends to take up too much space. Instead, use a figure caption when you copy and paste the chart into your word processor document. Above or underneath the graph, describe in 1 or 2 complete sentences what is being shown on the graph. Points should be large enough and distinctive to avoid possible confusion with any fly specks on the paper. If you are not using a computer, use a small dot surrounded by a circle, square, or triangle. The circle, square, or triangle around the dot are referred to as point protectors. If you are using Microsoft Excel, the default marker size should be okay. A smooth curve or best fit line should be drawn so that it comes as close as possible to passing through all the points. Do not connect the points by a series of straight line segments. One exception to the 2 preceding guidelines is if you have hundreds or thousands of very, very closely spaced points to show on the graph. You definitely need to use a computer program in this case. Set the marker size to 0 and simply connect the points with straight line segments. Finally, use legends only if you are plotting more than one dependent variable. In these cases, you should use different symbols to distinguish one variable from another. For example, you may use circles for one and triangles for the other. Here's an example of a very poorly constructed graph. Let's see if we can identify everything that's wrong with this graph. First of all, there's no label for the y-axis. The x-axis has a label length, but the units are not given. The interval size for the x-axis makes it very difficult to read the coordinates of points. It would be much better to mark intervals at 0.2, 0.4, 0.6, 0.8, and 1, or at 0.1, 0.2, 0.3, all the way up to 1. There is too much unused space in the plotted area. The y values for the points are shown all between 0 and 5, so there's no reason to extend the y-axis beyond 5. The markers for the points are a little too big. A legend is not necessary. Even if it was, the label shown is useless. This graph was created in Microsoft Excel. The label Series 1 is, in fact, used by Excel as a placeholder for a more descriptive name for the points shown. It is meant to be replaced by a more descriptive name. Finally, there is no descriptive title for the graph. The purpose of this experiment is to collect laboratory data that we can use to apply the lessons about graphing presented in earlier slides. We will study the effect of the length of a pendulum string on its period. The period of a pendulum is the time it takes for the pendulum to complete one cycle. You need to measure the diameter of the pendulum bob with a vernier caliper. Dividing the diameter by 2 gives you the radius of the spherical bob. Setting the pendulum string length to 1/10 of a meter. Pull out the bob at an angle of about 5 degrees from vertical, then release. Measure the time it takes for the bob to go through 100 cycles. You divide this by 100 to get the actual period. Repeat the procedure for longer strings by changing the length of the string. Here are some pictures and videos demonstrating the procedure for this experiment. Measure the diameter of the pendulum bob with a vernier caliper. Use the outer jaws of the caliper. You do not need to cut out various lengths of string for the pendulum. Simply tie the string to the mounting screw at appropriate sections in order to get the desired length. Put the excess length away from the bob. Measure the length of the string with a ruler or a meter stick after mounting it. Pull out the bob at an angle of about 5 degrees from vertical, then release. Start the timer at the same time you release the bob. Stop the timer when the bob completes 100 cycles. Turn the knob on the left side of the timer to reset the reading to 0. It can be shown that the square of the period of a pendulum is directly proportional to the length of the pendulum as measured from the center of the bob. In the equation shown here, T is the period of the pendulum. T is the time it takes for the pendulum to complete one cycle. L is the length of the pendulum as measured from the center of the bob. As you can see from the diagram, L is equal to the length of the string, which is indicated by L0, plus the radius of the bob, which is indicated with a capital R. The proportionality constant is 4 pi squared over g, where g is the acceleration due to gravity. For this experiment, our independent variable here is L0. Our dependent variable is the period, t. Since t is not equal to a constant times L0 plus another constant, the plot of t versus L0 will not give us a straight line. However, t squared is equal to a constant times L0 plus another constant. Therefore, a plot of t squared versus L0 will give us a linear trend, with the slope equal to 4 pi squared over g, and an intercept equal to 4 pi squared over g times the radius of the bob. Therefore, from our experimental slope, we can calculate the value of g. G will be equal to 4 pi squared divided by the slope. We expect this to be close to the known value of 9.8 meters per second squared. From the slope and y-intercept, we can calculate the radius of the bob. This should agree with the radius we calculated by dividing the measured diameter by 2. Linear regression is the process of determining the slope and intercept of the best fit line. With modern spreadsheet programs like Microsoft Excel, it is very easy to determine the slope and y-intercept of the best fit line. In the case of Excel, we simply format the trend line so that the equation of the line is displayed on the chart. The problem is that with this method, Excel does not always show the correct number of significant figures for the slope and y-intercept. It also does not tell us what the uncertainties are for the slope and y-intercept. Here we show an alternative procedure for determining the slope and y-intercept in Excel. This procedure will also allow you to determine the standard errors in the slope and y-intercept. First, we make sure that the Analysis Tool Pack add is installed. We click on Tools, then we click on Add-ins. The Add-ins window will pop up as shown here. Next, make sure that the boxed Analysis Tool Pack is checked. Then click OK. To do a linear regression, click on Tools. Then click on Data Analysis. Then scroll down the list of analysis tools and click on Regression. Then click OK. The regression window will pop up. In this window, you need to specify the locations of your x and y values. In the example shown here, the x values are in cells A2 through A6. So in the blank next to Input X Range, we type A2 colon A6. Also in this example, the y values are in cells B2 through B6. In the regression windows, there is a box next to the phrase constant is 0. You can check or uncheck this box depending on whether you want to force the value of the y-intercept to 0. When you click OK, the results will be shown on a new worksheet. Here's an example of the results of a regression analysis in Excel. As shown here, the y-intercept is given in cell B17, which is negative 0.01321, and the standard error in the y-intercept is in cell C17, which is 0.045312. We only keep the first non-zero digit in the standard error, so it should be rounded off at 0.05. We round off the y-intercept to the same number of decimal places as the standard error. Therefore, the intercept is negative 0.01 plus or minus 0.05. The slope is referred to as the coefficient of the x variable, and it is shown in this example in cell B18, right below the y-intercept. The slope is 0.226843. The standard error in the slope is given immediately to the right of the slope, in cell C18. The standard error is 0.013682. Since the first non-zero digit in the standard error is less than 3, we keep one extra digit. That is, the standard error should be reported as 0.014, and the slope should be reported to as many decimal places as the standard error. Therefore, the slope is 0.227 plus or minus 0.014.